In this video, we will learn how to understand pKa values and use them to predict acidity and calculate equilibrium constants. We will also discuss how to calculate and interpret formal charges, as well as how to depict the movement of electrons using arrow pushing. Let's begin with a review of the acidity constant, Ka. Ka is an equilibrium constant that measures the equilibrium between an acid, Ha, and its dissociation into H plus and its conjugate base, A minus. Mathematically, Ka equals the concentration of the products over the concentration of the reactants. Specifically, Ka equals the concentration of protons multiplied by the concentration of the conjugate base A minus divided by the concentration of the acid. A reaction's Ka is measured experimentally. Strong acids undergo complete or nearly complete dissociation in water. As a result, the concentrations of protons, H plus, and the conjugate base, A minus, are much higher than the concentration of the undissociated acid, HA, which leads to a large Ka value. Conversely, weak acids have incomplete dissociation in water, and as a result, the concentration of acid HA in solution is much higher than the concentrations of protons, H plus, and the conjugate base, A minus, which leads to a small Ka value. In summary, strong acids have large Ka values, Ka greater than 1, and weak acids have small Ka values, Ka less than 1. For simplicity, we often use pKa values instead of Ka. pKa is the negative logarithm of the acidity constant, Ka, and is typically more manageable to work with. While Ka values can span a very wide range from extremely small numbers for weak acids to very large numbers for strong acids, pKa values compress this range into a more convenient and intuitive scale. Because we're taking the negative log of Ka, higher pKa values correspond to weaker acids, molecules with a stronger H atom bond, while lower pKa values correspond to stronger acids, molecules with a weaker H atom bond. pKa values are very helpful for predicting which direction an acid-base equilibrium will favor, or in other words, which species will predominate at equilibrium. Consider the following example. HBr reacts with methoxide to give a bromide anion and methanol. We've already seen that most hydrohalic acids, HX, such as HCl, HBr, and HI, tend to be strong acids because their conjugate bases can stabilize negative charges well. Similarly, we've observed that alkoxides, such as methoxide, are strong bases due to the high electron density on the oxygen atom, which makes them highly reactive and able to readily accept protons. We also know that halides are weak bases and alcohols are relatively weak acids. Using our prior knowledge, we'd expect the forward reaction to be favorable and the species bromide and methanol to predominate at equilibrium. Now let's use pKa values to arrive at the same conclusion. The pKa of the acid HBr is negative 8.7, and the pKa of the conjugate acid methanol is 15.54. Most alcohols have a pKa between 16 and 18. Notice that in the forward reaction, we're going up in pKa value as we go from the stronger acid to the weaker acid. Consider a molecule's pKa value as an indicator of proton affinity. Molecules with a higher pKa have a higher proton affinity, or a stronger H atom bond, making them weaker acids. Conversely, molecules with a lower pKa have a lower proton affinity, or weaker H atom bonds, making them stronger acids. It is energetically favorable for a reaction to break weaker bonds to form stronger bonds. Therefore, acid-base reactions will favor the formation of the acid with the higher pKa value. Now we can say for sure that the forward reaction is favorable, but just how much more favorable is it? pKa values can also be used to quantify the favorability of a reaction. The pKa of HBr is negative 8.7, and the pKa of methanol is around 15.54, giving a difference of 24.24 pKa units. From this difference in pKa values, we can calculate the equilibrium constant Ka for the reaction using the equation 10 to the delta pKa. This gives us a value of 10 to the 24.24, indicating that the forward reaction is 10 to the 24.24 times more favorable, or in other words, more favorable by 24.24 orders of magnitude. Let's work through an example that's slightly less obvious. Acetylene reacts with sodium amide, NaNH2, to give sodium acetylide and ammonia. We can use the pKa values of the acid and conjugate acid in the forward reaction to predict the direction of the reaction. The pKa of acetylene is 25, and the pKa of ammonia in water is 37. Notice that in the forward reaction, we're going up in pKa value as we go from the stronger acid to the weaker acid. Considering the molecule's pKa values as an indicator of proton affinity, we can see that the HN bond formed in ammonia is stronger than the CH bond broken in acetylene. Because acid-base reactions favor the formation of the acid with the higher pKa value, we can predict that the forward reaction is more favorable, specifically by 12 orders of magnitude, or 10 to the 12 times more favorable. Although both acetylene and ammonia are weak acids, we can see that the forward reaction is overall favorable from the pKa values. At this point, we've discussed almost all there is to know about acid-base reactions. Finally, we will discuss their significance. Protonation and deprotonation affect electron density. When a neutral molecule is deprotonated and becomes its conjugate base, it gains a negative charge and becomes more electron-rich. Conversely, when a neutral molecule is protonated and becomes its conjugate acid, it gains a positive charge and becomes more electron-poor. Increasing or decreasing the electron density of a molecule has a drastic effect on its reactivity. In a chemical reaction, electron-rich areas are likely to be the source of electrons, and electron-poor areas are likely to be the sink or destination of those electrons. Oftentimes, the addition or removal of protons can result in formal charges. We can calculate an atom's formal charge using the formula Fc equals Ve minus Nbe plus B. In this equation, Ve represents the number of valence electrons the neutral atom has. From this number, we subtract the sum of the atom's non-bonding electrons, Nbe, and the number of bonds B the atom has. For example, we can use this equation to calculate the formal charge of the oxygen in hydronium H3O+. Oxygen has 6 valence electrons, so Ve equals 6. From there, we subtract the sum of the number of non-bonding electrons on oxygen, 2, and the number of bonds to other atoms, 3, giving us a final formal charge of +1. Let's use the equation one more time to calculate the formal charge of another molecule we're familiar with, ammonium, NH4+. Nitrogen has 5 valence electrons, VEE equals 5, has no non-bonding electrons, and forms 4 bonds. By plugging in these values, we find that the nitrogen in ammonium also has a formal charge of +1. It's important to recognize that formal charges do not account for the unequal sharing of electrons due to electronegativity. While we assign formal charges to oxygen and nitrogen, these positive charges do not indicate an empty orbital, as in the case of a carbocation ion. We assume that oxygen and nitrogen still have full octets. The differences in electronegativity between these atoms and hydrogen explain the unequal sharing of electrons, resulting in partial negative charges on oxygen and nitrogen and partial positive charges on the hydrogen atoms. Up until now, we've discussed how to predict which direction an acid-base reaction will favor and why, but we have not yet observed the movement of electrons that drive these reactions. In organic chemistry, we use arrow-pushing formalism to depict the movement of electron pairs in reactions to elucidate reaction mechanisms. In this formalism, a double-barbed arrow is drawn from an area of high electron density to an area of low electron density. The arrow originates from the non-bonding electrons on an electron-rich atom, and the point of the arrow is directed to the electron-poor atom. When drawing arrows, it's important to never draw an arrow from or to a charge. Arrows should always be drawn from the source of electrons, the non-bonding electron pair of the electron-rich atom, to the sink of electrons, the electron-poor atom. Let's revisit the examples of acid-base reactions we saw earlier in the video and depict the movement of electron pairs using arrow-pushing formalism. We can start by identifying the electron-rich and electron-poor species in this reaction. The methoxide ion has an electron-rich oxygen atom, which will be the source of electrons. Hydrogen bromide has an electron-poor hydrogen due to the unequal sharing of electrons in the hydrogen-bromine bond caused by the difference in electronegativity. This electron-poor hydrogen will be the sink or final destination of the electrons. Now we're ready to draw the arrows. The arrow starts from the non-bonding electron pair on the oxygen in methoxide and is drawn to the hydrogen in hydrogen bromide. Then, we draw one more arrow from the hydrogen-bromine bond to the bromine atom. With these arrows, we've indicated that the non-bonding electron pair on oxygen is used to form a bond with hydrogen, and the hydrogen-bromine bond breaks, returning the shared electrons in the bond to the bromine atom. This gives us our two products, methanol and the bromide anion. Let's do this one more time for the second acid-base reaction. We can start by identifying the electron-rich and electron-poor species. The azonide anion has an electron-rich nitrogen, which will be the source of electrons. Acetylene has a weakly acidic proton, which will be the sink or final destination of the electrons. Now we're ready to draw the arrows again. The arrow starts from the non-bonding electron pair on the nitrogen in azonide and is drawn to the weakly acidic proton in acetylene. Then we draw one more arrow from the hydrogen-carbon bond to the carbon atom. With these arrows, we've indicated the non-bonding electron pair on nitrogen is used to form a bond with hydrogen, and the hydrogen-carbon bond breaks, returning the shared electrons in the bond to the carbon atom. Finally, the sodium ion forms an ionic interaction with the newly formed carbanion, giving us our two products, sodium acetylide and ammonia. Even though acetylene is a symmetrical molecule and can be deprotonated from either side to give the same product, we do not observe deprotonation on both sides. This is because we treat acetylene with an equal equivalent of sodium amide, and also because having two carbanions triple bonded to each other is highly unstable. As always, let's do some practice. For each of the following reactions, predict which species will predominate at equilibrium. Additionally, for the favorable reaction, determine how favorable it is by identifying the number of orders of magnitude. Feel free to pause the video and try these problems on your own first. We can use the pKa values of the acid and conjugate acid in the forward reaction to predict which direction the reaction favors. The pKa of the acid, hydrogen iodide, is negative 9.3, and the pKa of the conjugate acid, protonated dimethyl ether, is negative 3.8. In the forward reaction, we're going up in pKa value as we go from the stronger acid to the weaker acid. Considering the molecule's pKa values as an indicator of proton affinity, we can see that the HO bond formed in protonated dimethyl ether is stronger than the HI bond broken in hydrogen iodide. Because acid-base reactions favor the formation of the acid with the higher pKa value, we can predict that the forward reaction is more favorable, specifically by 5.5 orders of magnitude. Again, for the second reaction, we can use the pKa values of the acid and conjugate acid in the forward reaction to predict which direction the reaction favors. The pKa of the acid, sulfuric acid, is negative 3, and the pKa of the conjugate acid, disopropylamine, is 11.07. In the forward reaction, we're going up in pKa value as we go from the stronger acid to the weaker acid. Considering the molecule's pKa values as an indicator of proton affinity, we can see that the HN bond formed in disopropylamine is stronger than the HO bond broken in sulfuric acid. Because acid-base reactions favor the formation of the acid with the higher pKa value, we can predict that the forward reaction is more favorable, specifically by 14.07 orders of magnitude. Let's move on to the next question. Use arrow-pushing formalism to illustrate the movement of electron pairs in the reactions from the previous question, as well as in the following Lewis acid-base reactions. Feel free to pause the video and try these problems on your own first. The first reaction is one we've seen already, ammonia reacting with boron trifluoride to form the ammonia-boron trifluoride complex. In this reaction, ammonia is the electron pair donor, or the Lewis base, and boron trifluoride is the electron pair acceptor, or the Lewis acid. Now that we've identified the electron-rich and electron-poor species, we're ready to draw the arrows. The arrow starts from the non-bonding electron pair on the nitrogen in ammonia and is drawn to the boron in boron trifluoride. With these arrows, we've indicated that the non-bonding electron pair on nitrogen is used to form a coordinate covalent bond with boron. This gives the nitrogen a formal charge of +1 and boron a formal charge of -1 in the resulting complex. In the second reaction, chlorine gas Cl2 reacts with aluminum trichloride to form an AlCl bond. In this reaction, one of the chlorine atoms in Cl2 acts as the Lewis base, and aluminum trichloride AlCl3 is the Lewis acid. We can draw an arrow starting from the non-bonding electron pair of one of the chlorine atoms in Cl2 to the aluminum in aluminum trichloride. With these arrows, we've indicated that the non-bonding electron pair on one chlorine atom is used to form a coordinate covalent bond with aluminum. This gives the chlorine a formal charge of +1 and aluminum a formal charge of -1. However, because chlorine is more electronegative than aluminum, there is unequal sharing of electrons in the bond, resulting in partial charges that the formal charge does not account for. Let's draw the arrow pushing for the Brunstad-Lowry acid-base reactions from the previous question. In the first reaction, the arrow starts from the non-bonding electron pair on the electron-rich oxygen in dimethyl ether and is drawn to the electron-poor hydrogen in hydrogen iodide. Then we draw one more arrow from the hydrogen iodide bond to the iodine atom. With these arrows, we've indicated that the non-bonding electron pair on oxygen is used to form a bond with hydrogen, and the hydrogen iodide bond breaks, returning the shared electrons in the bond to the iodine atom. This leaves us with our two products, protonated dimethyl ether and the iodide anion. In the second reaction, the arrow starts from the non-bonding electron pair on the electron-rich nitrogen in LDA, lithium diisopropylamide, and is drawn to the electron-poor hydrogen in sulfuric acid. Then we draw one more arrow from the hydrogen-oxygen bond to the oxygen atom. With these arrows, we've indicated that the non-bonding electron pair on nitrogen is used to form a bond with hydrogen, and the hydrogen-oxygen bond breaks, returning the shared electrons in the bond to the oxygen atom. This leaves us with our two products, lithium hydrogen sulfate and diisopropylamine. Let's move on to the next question. Calculate the formal charge of the colored atoms in each of the following molecules. Feel free to pause the video and try these problems on your own first. For the first molecule, ozone, let's start by calculating the formal charge of the oxygen on the left. Oxygen has 6 valence electrons. This oxygen atom has 6 non-bonding valence electrons and 1 bond to another atom. Using our formula, we find that this oxygen has a formal charge of -1. The middle oxygen in ozone also has 6 valence electrons, with 2 non-bonding valence electrons and 3 bonds to other atoms. Using our formula, we find that this oxygen has a formal charge of +1. Finally, the oxygen on the right has 6 valence electrons, with 4 non-bonding valence electrons and 2 bonds to another atom. Using our formula, we find that this oxygen has a formal charge of 0. For the second molecule, nitromethane, the oxygen on the top has 6 valence electrons, 4 non-bonding electrons, and 2 bonds to another atom. Using our formula, we find that this oxygen has a formal charge of 0. The nitrogen atom has 5 valence electrons, no non-bonding valence electrons, and 4 bonds to other atoms. Using our formula, we find that this nitrogen has a formal charge of +1. Finally, the oxygen on the bottom has 6 valence electrons, 6 non-bonding valence electrons, and 1 bond to another atom. Using our formula, we find that this oxygen has a formal charge of -1. In the third molecule, bromine has 7 valence electrons, 4 non-bonding valence electrons, and 2 bonds to other atoms. Using our formula, we find that bromine has a formal charge of +1. In the fourth molecule, nitrogen has 5 valence electrons, no non-bonding valence electrons, and 4 bonds to other atoms. Using our formula one last time, we find that nitrogen has a formal charge of +1. Finally, let's move on to our last question. When one equivalent of citric acid is titrated with excess trimethylamine, in what order are the functional groups deprotonated based on their pKa values? Consider whether all functional groups will be deprotonated. Feel free to pause the video and try to solve this problem on your own first. When titrating one equivalent of citric acid with excess trimethylamine, we need to consider the pKa values of the functional groups in citric acid to determine the order of deprotonation. Citric acid has 3 carboxylic groups with the following pKa values: 3.13, 4.76, and 6.40. Recall that lower pKa values correspond to greater acidity. Therefore, these 3 carboxylic acid functional groups will be deprotonated by trimethylamine in this order. Although trimethylamine is a strong enough base to deprotonate all 3 carboxyl groups, it is unlikely to deprotonate the hydroxyl group because its pKa is too high relative to the base strength of trimethylamine. The pKa of the hydroxyl group in citric acid is around 14.4, which is higher than the pKa of the conjugate acid of trimethylamine, which is around 9.8. Considering the molecule's pKa values as an indicator of proton affinities, we can see that the HO bond we are trying to break is stronger than the HN bond that would be formed. Therefore, because acid-base reactions favor the formation of the acid with the higher pKa value, we can predict that trimethylamine is unlikely to deprotonate the hydroxyl group. In summary, during the titration of citric acid with excess trimethylamine, the three carboxyl groups will be deprotonated in the order of their increasing pKa values, and the hydroxyl group will remain protonated. As always, thank you for watching, and I'll see you next time.